Nature built 6 different kinds of quarks. 6. Each one real, each one observed in experiments. They have names: up, down, charm, strange, top and bottom. 6 distinct building blocks sitting in the rulebook of particle physics. But here is the strange part. When nature actually constructs matter, when it assembles the atoms that make up your body, the air you breathe, the ground beneath your feet, every star, every planet, every grain of sand in the observable universe, it uses only 2. Just 2 out of 6. Up and down. That is it. The other 4 quarks exist. They have been detected. They are not theoretical, but they are almost completely absent from the world around you. So what happened to them? Why would the universe create 6 types of a fundamental particle and then build almost everything from only the lightest pair? Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now, let's begin. Look around you. Pick up anything: a pen, a rock, a glass of water. Hold it in your hand and consider what it actually is. Whatever you are touching right now is made of atoms. Your hand itself is made of atoms. The chair you are sitting in, the floor beneath it, the walls around you, the air filling the space between those walls. Atoms. Every single thing you have ever touched, tasted, seen, or smelled in your entire life is made of atoms. This is not some abstract statement about chemistry. It is the literal physical reality of everything you experience. The screen you are looking at right now, the food you ate this morning, the star that lights up our sky every morning, every distant sun twinkling in the night sky. Atoms. All of it. The universe, as far as we can tell, is built almost entirely from atoms. But atoms are not the end of the story. They are not the smallest pieces. For a long time, scientists believed they were. The very word atom comes from the ancient Greek word atomos, meaning uncuttable. About 2,400 years ago, Greek philosophers named Democritus and Leucippus proposed that if you kept cutting matter into smaller and smaller pieces, you would eventually reach a particle so small it could not be divided any further. That, they said, was the atom, the fundamental, indivisible building block of everything. They were half right. Matter is indeed made of discrete units, but those units are not indivisible. Atoms have parts. Those parts have parts. And if you keep going deeper, you eventually reach a place that raises one of the strangest questions in all of physics. An atom consists of 2 main regions. There is a cloud of electrons surrounding a central nucleus. The electrons are light, fantastically light. Each electron has a mass of roughly 9.1 times 10 to the negative 31 kilograms, which is so small that the number is essentially meaningless in everyday terms. What matters is that electrons are tiny compared to everything else in the atom. They carry negative electric charge, and they occupy a relatively enormous volume of space around the nucleus. If you scaled an atom up to the size of a football stadium, the electron cloud would fill the entire stadium. The nucleus, meanwhile, would be a small object sitting at the center of the field, maybe the size of a marble, maybe smaller. The atom is almost entirely empty space. If you could somehow remove all the empty space from every atom in a human body, compress all the nuclei and electrons down so there were no gaps, the entire body would fit into a space smaller than a speck of dust. You are mostly nothingness, held in structure by electromagnetic forces. But that tiny marble at the center contains nearly all the atom's mass. The nucleus is extraordinarily dense. It is made of 2 types of particles: protons, which carry positive electric charge, and neutrons, which carry no charge at all. These particles are collectively called nucleons because they live in the nucleus. The number of protons in a nucleus determines which element the atom is. 1 proton makes hydrogen, 2 protons make helium, 6 make carbon, 8 make oxygen, 26 make iron, 92 make uranium. Every element on the periodic table is defined entirely by how many protons sit in the nucleus of its atoms. Neutrons are almost identical to protons in mass, but have no electric charge. They play a critical role in holding the nucleus together. Without neutrons, the positively charged protons would repel each other through electromagnetic force, and the nucleus would fly apart. Neutrons provide additional binding without adding more repulsion. For decades, this was considered the deepest layer. Protons and neutrons were thought to be fundamental particles, meaning they had no internal structure. The uncuttable pieces that Democritus imagined. Physicists had identified them, measured their masses, and built successful theories around the assumption that protons and neutrons were the bottom of the ladder. Indivisible, end of story. Except it was not the end of the story. By the middle of the 20th century, there were hints that protons and neutrons might be more complicated than anyone expected. Particle accelerators were smashing atoms together at higher and higher energies, and every time physicists increased the collision energy, new particles kept appearing. Not just protons and neutrons, but dozens of other particles with strange properties and short lifetimes. There were pions and kaons and sigma particles and Z particles and eta particles. The list kept growing. By the 1960s, physicists had discovered so many supposedly fundamental particles that the situation became almost embarrassing. They called it the particle zoo. There was no obvious organizing principle, no clean pattern. It was as if physicists had opened a box, expecting to find a few simple pieces, and instead found hundreds of components with no instruction manual. Something deeper had to be going on. In 1964, 2 physicists independently proposed a radical idea. Murray Gell-Mann at the California Institute of Technology and George Zweig at CERN both suggested that the zoo of particles was not fundamental at all. All those dozens of particles were themselves made of even smaller components. Gell-Mann called these components quarks, a whimsical name borrowed from a passage in James Joyce's novel Finnegan's Wake. Zweig called them aces. The physics community adopted Gell-Mann's terminology, and the name stuck. The original proposal suggested 3 types of quarks: up, down, and strange. By combining quarks in different arrangements, you could account for every particle in the zoo. 3 quarks bound together made a baryon, a category that includes protons and neutrons. A quark paired with an antiquark made a meson, the category that includes pions and kaons. The mathematics was elegant, the patterns were beautiful. Every known particle fit into the scheme. But there was a problem. Nobody had ever seen a quark directly. The theory predicted them. The math required them. But no experiment had isolated one, or directly confirmed that protons had internal structure. That changed in the late 1960s at the Stanford Linear Accelerator Center, known as SLAC. The experiment was conceptually simple, though technically extraordinary. Physicists fired a beam of high-energy electrons at protons and watched what happened. The electrons were accelerated to nearly the speed of light and slammed into stationary proton targets. Detectors measured where the electrons went after the collision and at what angles they emerged. If a proton were a uniform blob of matter, the electrons would scatter smoothly. But that is not what the experimenters saw. Some electrons bounced back at steep angles, as if they had struck something small and hard inside the proton. The pattern was unmistakable. The proton was not a smooth, uniform object. It contained small, dense, point-like particles rattling around inside it. This was deep inelastic scattering, and it provided the first direct experimental evidence that protons have internal structure. The physicists leading the experiment, Jerome Friedman, Henry Kendall, and Richard Taylor, would later receive the Nobel Prize for this discovery. Richard Feynman, one of the most brilliant physicists of the 20th century, initially called these internal constituents partons, a generic term meaning simply the parts inside a proton. It soon became clear that Feynman's partons were exactly the quarks that Gell-Mann and Zweig had predicted 4 years earlier. The theory was confirmed. Protons and neutrons are not fundamental. They are composite objects built from quarks. So what exactly is inside a proton? 2 up quarks and 1 down quark. That is it. 3 quarks bound together so tightly that under normal circumstances they can never be separated. A neutron is almost identical in structure, but with one swap. It contains 1 up quark and 2 down quarks. The difference between a proton and a neutron, the difference between a positively charged particle and a neutral one, comes down to exchanging a single up quark for a single down quark. That is remarkably elegant. 2 types of quarks, arranged in groups of 3, produce the 2 particles that make up every atomic nucleus in the universe. But what holds them together? The electromagnetic force cannot do it. Up quarks carry an electric charge of plus 2/3, and down quarks carry a charge of minus 1/3. If you add up the charges in a proton, you get plus 2/3, plus 2/3, minus 1/3, which equals plus 1. For a neutron, plus 2/3, minus 1/3, minus 1/3 gives 0. But electrically, 2 of the 3 quarks in a proton carry the same sign of charge. They should repel each other. The electromagnetic force would tear the proton apart, not hold it together. The force binding quarks is something else entirely. It is called the strong nuclear force, and it is carried by particles called gluons. If you have heard of photons, the particles that carry the electromagnetic force, then gluons are their equivalent for the strong force. But gluons are far stranger than photons in one crucial way. Photons carry no electric charge themselves. They transmit the electromagnetic force between charged particles, but they do not interact with each other directly. A beam of light can pass through another beam of light without either beam being affected. Gluons are different. They carry what physicists call color charge, and because they carry color charge, gluons interact with other gluons. This makes the strong force vastly more complicated than electromagnetism and gives it properties that are unlike anything in everyday experience. Color charge has nothing to do with actual colors. It is a label physicists use to describe a property of quarks that has no everyday analogy. Each quark carries one of 3 color charges, whimsically named red, green, and blue. Antiquarks carry anticolors. Gluons carry combinations of color and anticolor. And here is the crucial rule. In nature, only color-neutral combinations are allowed to exist as free particles. 3 quarks, 1 red, 1 green, 1 blue, combine to make a color-neutral baryon. A quark and an antiquark with matching color and anticolor combine to make a color-neutral meson. You cannot isolate a single quark because a single quark carries a net color charge, and isolated color charges are forbidden by the rules of the strong force. This property is called confinement. Quarks are permanently confined inside composite particles called hadrons. If you try to pull 2 quarks apart, the strong force between them does not weaken with distance the way electromagnetism does. Instead, it stays constant or even increases. The energy stored in the gluon field between the separating quarks grows and grows until there is enough energy to create a brand new quark-antiquark pair from the vacuum itself. Instead of freeing a quark, you have created new quarks. The original quarks remain confined. You end up with more hadrons, never with a naked quark. This is why no one has ever detected an isolated quark, and almost certainly no one ever will. Quarks always come packaged in groups. This phenomenon has a dramatic consequence worth pausing on. The total mass of the 3 quarks inside a proton, 2 ups and 1 down, adds up to only about 10 mega-electron volts. But the proton itself has a mass of about 938 mega-electron volts. That means over 99% of the proton's mass does not come from the quarks themselves. It comes from the energy of the gluon field binding them together. Einstein's famous equivalence of mass and energy is not just theoretical here. It is literally what gives you most of your weight. The energy of the strong force, converted into mass through that equivalence, accounts for the vast majority of the mass of every atom in your body. You are not mostly made of quarks by mass. You are mostly made of the energy that holds quarks together. The theory describing all of this, the strong force, gluons, color charge, and confinement, is called quantum chromodynamics. The name literally means the quantum dynamics of color. It is one of the most mathematically complex and successful theories in all of physics. It explains how quarks bind together, why protons and neutrons have the masses they do, and why nuclear matter behaves the way it behaves. It has been tested against experimental data thousands of times and has never been contradicted. Now here is where the story takes its most surprising turn. Up and down quarks are not the only quarks that exist. They are the lightest. They are the most common. They are the ones that build protons and neutrons, and therefore atoms, and therefore everything you see around you. But they are only 2 members of a family of 6. The 6 quark flavors, as physicists call them, are arranged in 3 pairs called generations. The first generation contains the up quark and the down quark. These are the familiar ones, the ones inside every proton and neutron. The up quark has a mass of roughly 2 mega-electron volts. The down quark is slightly heavier, at roughly 4.7 mega-electron volts. Both are extraordinarily light by particle physics standards. Together, they form the foundation of all ordinary matter in the universe. The second generation contains the charm quark and the strange quark. The strange quark has a mass of about 95 mega-electron volts, making it roughly 20 times heavier than the down quark. The charm quark is heavier still, at about 1.27 giga-electron volts. That is more than 600 times the mass of an up quark. These are not small differences. The jump from the first generation to the second is enormous in terms of mass. The charm quark outweighs the up quark the way a grown adult outweighs a small insect. Same type of particle, same fundamental rules, same electric charge, but vastly, dramatically more massive. The third generation is where things become truly extreme. The bottom quark has a mass of about 4.18 giga-electron volts. It is nearly 900 times heavier than the down quark, its first generation counterpart. And then there is the top quark. The top quark is a monster. It has a mass of approximately 173 giga-electron volts. That is roughly 80,000 times heavier than the up quark.
To put this in perspective, the top quark is about as heavy as an entire atom of tungsten, one of the densest metals on the periodic table. A single fundamental particle with the mass of an entire atom. The top quark is by far the heaviest known fundamental particle in nature. Nothing else comes close. It is so massive that when it was finally discovered, physicists had to build one of the most powerful particle accelerators on the planet just to produce enough energy to create one. And even then, Top quarks appeared only rarely among billions of collisions. Each generation mirrors the electric charge structure of the one before it. In every pair, one quark carries a charge of plus 2/3 and the other carries minus 1/3. Up is plus 2/3. Down is minus 1/3. Charm is plus 2/3. Strange is minus 1/3. Top is plus 2/3. Bottom is minus 1/3. The pattern repeats perfectly across all three generations. The charges are identical. The interactions with the strong force are identical. The way they combine to form hadrons is identical. The only difference is mass. It is as if nature designed 3 copies of the same blueprint, but built each successive copy from heavier and heavier materials. All 6 flavors are equally real. All 6 have been experimentally detected. All 6 interact through the strong force, form composite particles, and obey quantum chromodynamics. All 6 are required by the mathematical framework known as the Standard Model, which is the most successful and thoroughly tested theory in the history of physics. The Standard Model describes every known fundamental particle and 3 of the 4 fundamental forces, and it requires exactly 6 quarks arranged in exactly 3 generations, not 5, not 7, 6. The mathematics demands it, and experiment confirms it. And yet almost none of the matter around you contains charm quarks, strange quarks, bottom quarks, or top quarks. Your body is made of atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of up quarks and down quarks. End of list. The other 4 flavors are nowhere to be found in ordinary stable matter. Not in rocks, not in water, not in the air, not in the sun, not in distant stars, not in planets orbiting those stars. Everywhere you look in the observable universe, stable matter is built from the 2 lightest quarks and nothing else. This is genuinely puzzling if you think about it carefully. The universe created 6 types of quarks. It wrote the laws of physics in a way that requires 6 types of quarks. Every quark flavor interacts through the same strong force, obeys the same quantum chromodynamic rules, and can combine with other quarks to form composite particles. There is no law of physics that says you cannot build a baryon using a charm quark instead of an up quark. You absolutely can. Physicists have done exactly that in particle accelerators. Those particles exist. They are real. They form, they interact, and then, almost instantly, they vanish. That is the key word. Vanish. The heavier quarks do not stick around. They appear, exist for an unimaginably brief moment, and then decay into lighter particles. They transform. They shed their excess mass and become something lighter, something more stable. Every charm quark eventually becomes something containing up and down quarks. Every strange quark does the same. Every bottom quark, every top quark. No matter how they are produced, no matter how much energy goes into creating them, no matter where in the universe the process takes place, the result is always the same. The heavy quarks decay, and what remains at the end of the chain is up quarks and down quarks, arranged into protons and neutrons. This is not a minor detail. It is not a footnote in a physics textbook. This is the central answer to the question we started with. The reason ordinary matter is built from only 2 of the 6 quark flavors is not because the other 4 are imaginary or unimportant or somehow less real. It is because the other 4 are unstable. They cannot persist. They are born and they die, over and over, in every high-energy environment where they appear. The only quarks that survive long enough to build atoms, to form nuclei, to construct the solid, tangible matter you interact with every moment of every day, are the 2 lightest ones, up and down. the survivors, the last quarks standing at the bottom of an enormous cascade of transformations that strips away everything heavier and leaves behind only what the universe allows to endure. But understanding why this happens, understanding the precise mechanism by which heavy quarks disappear and light quarks endure, requires us to explore something most people have never heard of: a force of nature that operates invisibly inside every atom. A force that does not hold things together or push things apart in the way you might expect. Instead, it does something far stranger. It reaches into a particle and changes its fundamental identity. It transforms one type of quark into another. This force has a name. It is called the weak force, and it is the reason 4 of the 6 quarks never get to participate in building the world around you. We said that 6 quark flavors exist, but only 2 build the ordinary matter around you. We said the answer has to do with stability, with mass, and with transformation. Now we need to understand exactly how that works, because the mechanism behind it is one of the most extraordinary processes in nature. It is a force that does not push, it does not pull, it does not hold things together or keep them apart. Instead, it changes what things are. It reaches into a particle and rewrites its identity at the most fundamental level. To understand why 4 quarks are missing from the everyday world, we need to understand this force, and we need to understand why mass determines everything about a particle's fate. Let us start with the masses themselves, because the differences between quark flavors are not subtle. They are staggering. We have already seen the numbers. The up quark at roughly 2 mega-electron volts, the down quark at roughly 5. Then a sharp climb. The strange quark is about 20 times heavier than the down. The charm quark is over 600 times heavier than the up. The bottom quark is nearly 900 times heavier than the down. And the top quark, the heavyweight champion of the particle world, sits at approximately 173 giga-electron volts. These are not gentle increments. The jump from one generation to the next is enormous. Each successive pair is not merely heavier than the one before it, it is vastly, overwhelmingly heavier. The pattern is not linear. It is not even simply exponential. It is a staircase where each step is hundreds or thousands of times taller than the last. And nobody knows why the staircase is shaped this way. Let me put that range into perspective. From the lightest quark to the heaviest, the mass increases by a factor of roughly 80,000. Imagine standing next to a house cat. That cat might weigh about 5 kilograms. Now multiply that by 80,000. You get 400,000 kilograms. That is the mass of a fully loaded Boeing 747 aircraft. The ratio between an up quark and a top quark is like the ratio between a house cat and a jumbo jet. Same basic category of object, same type of thing, but separated by an almost absurd difference in scale. Nobody fully understands why the masses are arranged this way. Nobody knows why 6 flavors exist, or why they fall into this particular pattern. It is one of the deepest unsolved questions in fundamental physics. The Standard Model can accommodate these masses, but it does not explain them. It takes them as inputs, measured values that must be determined by experiment. Why the top quark is nearly 100,000 times heavier than the up quark remains a mystery. But the consequences of this mass hierarchy are not mysterious at all. They are precise, measurable, and devastating for any heavy quark that hopes to survive. In nature, heavy things decay into lighter things when the laws of physics allow it. This is not a tendency or a preference. It is an inevitability driven by the deepest principles of physics. Energy flows downhill. Systems evolve toward lower energy states. A ball on top of a hill rolls down if nothing stops it. A hot object cools if nothing heats it. And a heavy particle, if there exists a lighter combination of particles it can transform into, will eventually make that transformation. It has no choice. The laws of quantum mechanics guarantee it. It might appear stable if you glance at it quickly, but it is not stable. It is merely waiting. And the heavier it is compared to the particles it can decay into, the faster it falls. This is where the weak force enters the picture. Of the four fundamental forces in nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, only one can change the flavor of a quark. Only one can reach into a hadron and transform an up quark into a down quark, or a charm quark into a strange quark, or a top quark into a bottom quark. That force is the weak force. The strong force binds quarks together, but it cannot change what kind of quark something is. Electromagnetism pushes and pulls charged particles, but it leaves their identity intact. Gravity curves space-time around massive objects, but it does not care what flavor of particle is doing the curving. Only the weak force has the power to alter a quark's flavor. It is the only force in nature that performs this particular trick. The weak force operates through two carrier particles called the W boson and the Z boson. The W boson comes in two versions, W plus and W minus, carrying positive or negative electric charge. The Z boson is electrically neutral. These bosons are the messengers of the weak force, just as photons are the messengers of electromagnetism and gluons are the messengers of the strong force. But W and Z bosons are dramatically different from photons in one crucial respect. They are massive, enormously massive by particle physics standards. The W boson has a mass of about 80.4 giga-electron volts. The Z boson is even heavier, at about 91.2 giga-electron volts. Photons, by contrast, are massless. They have zero mass. This difference in mass is the reason the weak force behaves so differently from electromagnetism. Electromagnetism has infinite range because its carrier, the photon, is massless and can travel any distance. The weak force has an extremely short range because its carriers are heavy and expensive in energy terms to produce. They can only exist for a fantastically brief moment before the uncertainty principle demands they disappear. This makes the weak force weak at low energies. It acts only at distances smaller than the nucleus of an atom. But within that tiny range, it does something no other force can do. It changes identities. Here is how it works. Imagine a charm quark sitting inside a composite particle. The charm quark has a mass of about 1.27 giga-electron volts. That is far heavier than an up quark or a down quark. The charm quark is unstable. The laws of physics allow it to transform into a lighter quark by emitting a W boson. The charm quark, with its electric charge of plus 2/3, emits a W plus boson and becomes a strange quark, which has a charge of minus 1/3. The charges balance perfectly. Plus 2/3 equals minus 1/3 plus 1. The W plus boson carries away the charge difference. Now, if you are paying close attention, something about this process should bother you. The charm quark has a mass of about 1.27 giga-electron volts. The W boson has a mass of about 80.4 giga-electron volts. How can a particle emit something more than 60 times heavier than itself? That seems to violate the most basic rule in physics. You cannot create energy from nothing. You cannot produce a particle far more massive than the one emitting it. And yet, this is exactly what happens. The answer lies in the Heisenberg uncertainty principle, one of the foundational rules of quantum mechanics. The uncertainty principle tells us that energy and time are linked by a fundamental trade-off. The shorter the time interval, the larger the energy fluctuation that nature permits. For extremely brief moments, particles can borrow energy from the vacuum itself, as long as they pay it back quickly enough. The W boson produced in a charm quark decay is not a real, stable particle in the way a photon from a flashlight is real. It is what physicists call a virtual particle. It exists for an almost immeasurably short time, far too brief to ever be directly observed, And during that flicker of existence, the normal rules of energy bookkeeping are temporarily relaxed. Think of it this way. Imagine you have $10 in your bank account, but you need to make a purchase of $1,000. Normally, you cannot do this. The transaction would be declined. But imagine a bank with a special rule. If you can complete the entire purchase and return the money within a single second, the bank will look the other way. It will not flag the overdraft because the discrepancy existed for such a short time that it never appeared on any statement. The larger the overdraft, the faster you must complete the transaction. A small overdraft gives you a little more time. A massive overdraft must be resolved almost instantly. This is roughly how virtual particles work. The W boson produced in a charm quark decay is enormously overdrawn on the energy budget. It is far heavier than the energy formerly available from the decaying quark. But it exists for such an extraordinarily brief time, roughly 3 × 10⁻25 seconds, that the uncertainty principle permits the overdraft. During that fleeting instant, the virtual W boson does its job. It carries away the charge and the flavor-changing quantum numbers. Then it decays into lighter particles, real particles that do satisfy normal energy conservation. The books balance when you look at the initial state, the charm quark, and the final state, the resulting lighter quarks or leptons. Energy is conserved overall. It is only during the unmeasurably brief intermediate step that the rules appear to bend. This is not a loophole or an approximation. It is how the weak force actually operates. Every flavor-changing decay in the universe proceeds through a virtual W boson. The W boson is never produced as a free, long-lived particle in these decays. It cannot be. There is not enough energy available. Instead, it flickers into existence as a quantum intermediary, facilitates the transformation, and vanishes. The entire process is described with extraordinary precision by quantum field theory, and the calculations match experimental measurements to many decimal places. Virtual particles are not a convenient fiction. They are an essential feature of how forces work at the quantum level. This virtual nature of the W boson is also the deeper reason the weak force is weak. Because the W boson is so heavy, about 80 times the mass of a proton, producing one even virtually is energetically expensive. The probability of a virtual W boson mediating a transition decreases sharply as the mass of the W boson increases relative to the energy available in the decay. If the W boson were lighter, weak decays would happen much faster. If it were massless like the photon, the weak force would be comparable in strength to electromagnetism. The weakness of the weak force is not some intrinsic timidity. It is a direct consequence of the W boson's enormous mass, making virtual production difficult and short-lived. The heavier the intermediary, the harder it is to borrow the energy, even briefly, and the slower the resulting process. But the W boson is itself extremely heavy and extremely unstable. It cannot travel any meaningful distance. Almost immediately, within roughly 3 × 10⁻25 seconds, the W boson decays into lighter particles. It might decay into a pair of lighter quarks, an up quark and an anti-down quark, for instance. Or it might decay into a charged lepton and a neutrino. The specific products depend on probability and available energy. But the W boson always decays. It never survives. It is a fleeting intermediary, a brief spark of energy that facilitates the transformation and then vanishes. So the sequence is this. A charm quark emits a W boson and becomes a strange quark. The W boson itself decays into lighter particles almost instantly. But the process does not stop there. The strange quark is also heavier than up and down quarks. It too is unstable. It will eventually undergo its own weak decay, emitting another W boson and transforming into an up quark. That up quark is light enough to be stable. It has nowhere further to fall.
It sits at the bottom of the mass hierarchy, or very close to it, and there is no lighter quark for it to decay into. The cascade ends. The heavy charm quark has been converted through a chain of weak force transformations into light quarks that can persist indefinitely. This cascading decay is not unique to the charm quark. It happens to every heavy quark. A bottom quark decays through the weak force, typically into a charm quark by emitting a W- boson. That charm quark then decays into a strange quark. The strange quark decays into an up quark. Each step sheds mass. Each step moves down the generational ladder. Each step is mediated by the weak force and its heavy W boson. And each step is irreversible under normal conditions, because the universe favors lower energy states. The cascade always moves in one direction, heavy to light, never the other way. Not unless you inject enormous energy to push it back uphill, which is exactly what particle accelerators do. Now let us talk about the most extreme case, the top quark, because the top quark illustrates this principle more dramatically than any other particle in nature. The top quark has a mass of approximately 173 giga-electron-volts. It is the heaviest known fundamental particle. And it is so heavy that something remarkable happens. It decays before the strong force can bind it into a hadron. Let me explain why that matters. Normally, when a quark is produced, the strong force immediately begins the process of confinement. Gluons stretch between the new quark and other quarks or antiquarks in its vicinity. Within roughly 10 to the negative 23 seconds, the strong force has done its work. The quark is packaged inside a composite particle, a proton, a meson, some kind of hadron. This happens incredibly fast. 10 to the negative 23 seconds is not a timescale that has any meaning in everyday life. It is far shorter than any human experience. But for the top quark, it is not fast enough. The top quark decays in roughly 5 times 10 to the negative 25 seconds. That is roughly 20 times faster than the strong force can bind it. The top quark appears, exists for an almost inconceivably brief moment, and then decays through the weak force into a bottom quark and a W boson before a single gluon can finish forming a bond. The strong force, the most powerful force in the universe at short distances, is too slow to catch the top quark before it is gone. This makes the top quark unique among all 6 flavors. It is the only quark that never forms a hadron under any observed circumstances.
Every other quark, no matter how briefly it lives, exists long enough to be confined inside a composite particle. The top quark does not. It is born naked and it dies naked, transforming into lighter particles before the universe can clothe it in the gluon field that binds every other quark. This is a stunning fact. The strong force is not some gentle, slow process. It is the most powerful interaction in nature. It holds atomic nuclei together against the electromagnetic repulsion of protons. It confines quarks so effectively that no quark has ever been observed in isolation. And yet the top quark is so unstable, its mass so enormous compared to the particles it can decay into, that it outruns the strong force entirely. It decays through the weak force, supposedly the weakest of the relevant interactions, faster than the strong force can act. This happens because the top quark's decay is not really limited by the weakness of the weak force. It is driven by the enormous mass difference between the top quark and its decay products. The larger the mass difference, the faster the decay. And for the top quark, the mass difference is colossal. 173 giga-electron-volts, dropping to about 4 giga-electron-volts for the bottom quark, with the rest carried away by the W boson and its subsequent decay products. There is so much energy available for the transition that it happens with extraordinary speed. Now contrast this with the up and down quarks. These are the lightest quarks. The up quark has a mass of roughly 2 MeV. There is no lighter quark for it to decay into. The decay process requires a destination, a lighter particle to become, and for the up quark, there is no such destination. It sits at the bottom of the mass ladder. It has nowhere to fall. The same is essentially true for the down quark in most practical contexts. While the down quark is slightly heavier than the up quark, the mass difference between them is only about 2.7 MeV. This tiny difference does allow a very specific transformation to occur, but only under certain conditions. We will return to this point shortly, because it connects to something important about neutrons. But the key insight right now is this. Up and down quarks are stable, or effectively stable, because they are the lightest quarks. Heavy quarks decay through the weak force into lighter quarks. The cascade always terminates at up and down. These two flavors are the final destination, the end of the road, the bottom of the hill. Everything heavier rolls down to them, and they remain. But you might wonder about the details. How does nature decide which specific decay path a heavy quark follows? Can a top quark skip the bottom quark and decay directly into a strange quark or even a down quark? The answer is yes, it can. But the probabilities are not equal for all transitions. In the 1960s and 70s, physicists discovered that quark flavor transitions through the weak force are governed by a set of probabilities encoded in a mathematical structure called the Cabibbo-Kobayashi-Maskawa matrix, often shortened to the CKM matrix. This matrix is named after three physicists, Nikola Cabibbo, Makoto Kobayashi, and Toshihide Maskawa, who developed the framework across several key papers. Each entry in the CKM matrix represents the probability amplitude for one quark flavor to transform into another through the weak force. Not all transitions are equally likely. Some are strongly favored, others are heavily suppressed. A top quark decaying into a bottom quark is highly probable, nearly 100% of the time. A top quark decaying directly into a strange quark is much rarer. A top quark decaying directly into a down quark is rarer still. Similarly, a charm quark preferentially decays into a strange quark, not into a down quark, though the latter does happen occasionally. The CKM matrix determines these preferences. It is measured experimentally with high precision, and it governs every flavor-changing process in the universe. The CKM matrix also has a beautiful property. It is unitary, meaning the total probability across all possible transitions always adds up to 1. A top quark must decay into something. It will become a bottom quark, a strange quark, or a down quark. The probabilities for these three options sum to exactly 100%. Nature keeps its books balanced. Nothing is lost. But the overwhelming preference is for transitions within the same generation or to the nearest neighboring generation. Cross-generational transitions, like a top quark becoming a down quark directly, are suppressed. They happen, but rarely. This is why decay cascades tend to proceed step by step down the generational ladder, rather than jumping directly to the bottom. Let us trace a complete example to make this concrete. A bottom quark is produced in a high-energy collision. It has a mass of about 4.18 giga-electron-volts. The CKM matrix tells us that the bottom quark most frequently decays into a charm quark by emitting a W- boson. The charm quark, now at about 1.27 giga-electron-volts, itself decays into a strange quark by emitting a W+ boson. The strange quark, at about 95 mega-electron-volts, decays into an up quark. Each step moves down in mass. Each step is mediated by the weak force. Each step produces a W boson that immediately decays into lighter particles. And at the end of the chain, you have an up quark sitting comfortably at the bottom of the mass hierarchy, stable and permanent. The entire process, from the creation of the bottom quark to its eventual conversion into an up quark, takes a tiny fraction of a second. A B meson lives for roughly 1.5 times 10 to the negative 12 seconds. A D meson lives for roughly 1 times 10 to the negative 12 seconds. A kaon lives for roughly 1 times 10 to the negative 8 seconds, considerably longer, but still unmeasurably brief by human standards. These are not timescales you can experience. They happen inside particle detectors, inside cosmic ray showers, inside the fireballs of colliding atomic nuclei. They happen, and they finish before a beam of light could cross the width of a single atom. Now let us return to the point about down quarks and neutrons, because it reveals something beautiful about the boundary between stability and instability. A neutron contains one up quark and two down quarks. A proton contains two up quarks and one down quark. The down quark is slightly heavier than the up quark, and indeed, a free neutron, one that is not bound inside an atomic nucleus, is unstable. It undergoes beta decay. One of its down quarks emits a W- boson and transforms into an up quark. The W- boson immediately decays into an electron and an antineutrino. The neutron has become a proton. This process was actually the first example of weak force physics ever studied, long before anyone knew quarks existed. Enrico Fermi developed the first theory of beta decay in 1933, decades before the quark model was proposed. He described the process as a neutron transforming into a proton while emitting an electron and a neutrino. He did not know about quarks or W bosons at the time. He could not have. But his mathematical description was remarkably accurate and laid the groundwork for our modern understanding of the weak force. A free neutron has an average lifetime of about 14 minutes and 40 seconds. That is extraordinarily long by particle physics standards. Most unstable particles decay in tiny fractions of a second. The neutron lives for almost 15 minutes. The reason is the mass difference between the neutron and the proton is tiny. The neutron has a mass of about 939.6 mega-electron volts. The proton has a mass of about 938.3 mega-electron volts. The difference is only about 1.3 mega-electron volts. That is a minuscule energy gap, and in the weak force, the rate of decay depends heavily on how much energy is available for the transition. More energy means faster decay. Less energy means slower decay. The neutron's decay is slow because there is barely enough energy to produce the electron and antineutrino that must accompany the transformation. The phase space, the range of possible outcomes for the decay products, is extremely limited. The decay is allowed, but just barely, and so it happens slowly. But here is the crucial twist. Inside an atomic nucleus, neutrons are stable. When a neutron is bound to protons through the strong force inside a nucleus, the binding energy changes the energy accounting. The mass of the bound system is lower than the mass of its individual components because binding energy has been released. In many nuclei, the bound neutron actually has less total energy than a free proton would have if it replaced the neutron. The decay is no longer energetically favorable. The neutron cannot decay because there is no lower energy state for it to fall into. The binding energy of the nucleus stabilizes the neutron. It pins the neutron in place, prevents the weak force from doing its work, and allows the neutron to persist for the lifetime of the nucleus itself. Consider a specific example. A helium-4 nucleus, also called an alpha particle, contains 2 protons and 2 neutrons. The total mass of 2 free protons and 2 free neutrons if you weighed them individually and added the results, would come to about 3,755.8 mega-electron volts. But the actual measured mass of a helium-4 nucleus is about 3,727.4 mega-electron volts. The difference, roughly 28.4 mega-electron volts, is the binding energy. That energy was released when the nucleus formed, carried away by photons and kinetic energy. And now, to break the nucleus apart, you would have to put all of that energy back in. The helium-4 nucleus is locked together. Each neutron inside it sits in an energy well so deep that the 1.3 mega-electron volts available from beta decay is nowhere near enough to climb out. The neutron cannot decay because the energy cost of disrupting the nuclear binding far exceeds the tiny energy gained from the neutron to proton mass difference. The nucleus forbids the transition. This creates a remarkable situation. A free neutron drifting alone through empty space is a ticking clock. It will decay within minutes. But capture that same neutron inside a helium nucleus, and it becomes one of the most stable configurations in all of nature. Helium-4 nuclei produced in the first few minutes after the Big Bang are still intact today, nearly 14 billion years later. The same particle that cannot survive 15 minutes on its own can last for the entire age of the universe when surrounded by the right neighbors. Context is everything. The depth of this energy well varies from nucleus to nucleus. In some nuclei, the binding is so tight that both protons and neutrons are locked in permanently. In others, the balance is more delicate. Certain isotopes have neutrons sitting in shallow energy wells where the binding energy barely exceeds the energy available from beta decay. These nuclei are radioactive. Their neutrons can decay because the energy accounting just barely permits it. This is why some elements have stable isotopes and unstable isotopes. The difference is not in the neutrons themselves. Every neutron in the universe is identical. The difference is in how deeply each neutron is embedded in the nuclear energy landscape. A neutron buried deep inside a tightly bound nucleus is safe. A neutron perched near the rim of a loosely bound nucleus is vulnerable. The weak force is always waiting, always ready to transform a down quark into an up quark. Whether it succeeds depends entirely on whether the surrounding energy landscape allows the transition. This interplay between the strong force and the weak force is one of the most elegant balancing acts in all of physics. The strong force builds the prison. The weak force tries to pick the lock. In stable nuclei, the prison walls are too thick. In radioactive nuclei, the walls are thin enough for the weak force to occasionally succeed. The boundary between stability and radioactivity, between matter that lasts forever and matter that transforms before your eyes, comes down to this quiet competition between two forces operating at completely different strengths and ranges, locked in a perpetual struggle inside every atomic nucleus in the universe. This is why matter is stable. Protons are stable because there is no lighter baryon for them to decay into under normal physics. They sit at the absolute bottom of the baryon mass hierarchy. Neutrons, which would be unstable on their own, are stabilized inside nuclei by the strong force's binding energy. Together, protons and neutrons form nuclei that can last for billions of years, which gives atoms time to form, which gives molecules time to assemble, which gives stars time to burn, which gives planets time to cool, which gives life time to evolve. The entire existence of stable matter in the universe depends on two quarks being lighter than the other four, on the weak force being the only interaction that can change flavor, and on nuclear binding energy being strong enough to stabilize the neutron. Remove any one of these conditions, and matter as we know it would not exist. If the down quark were much lighter than the up quark, instead of slightly heavier, protons would decay into neutrons, and atoms would have no stable positively charged nuclei to hold electrons. If the weak force did not exist, heavier quarks would never decay, and the universe would be flooded with unstable particles that could never form atoms. If the strong force were slightly weaker, nuclei could not hold together, and there would be no stable atoms beyond hydrogen. The stability of ordinary matter is not a given. It is the result of a specific and delicate arrangement of masses, forces, and decay rules that happen to produce a universe where up and down quarks, and only up and down quarks, survive long enough to build everything you see. So the answer to our central question is taking shape. The universe has 6 quarks, but ordinary matter uses only 2, because the other 4 are too heavy to last. They decay through the weak force, cascading down the mass ladder through a series of transformations governed by the CKM matrix, shedding mass at every step until only up and down quarks remain. The top quark cannot even form a composite particle before it decays. The bottom, charm and strange quarks form particles that exist for vanishingly brief moments before transforming into lighter ones. The up and down quarks, sitting at the bottom of the hierarchy, have nowhere further to fall. They are the end of every decay chain, the last quarks standing. But this raises an obvious question. If heavy quarks are so unstable, if they decay so quickly, where do they actually show up? If they are not in ordinary matter, where are they? The answer is that they appear wherever there is enough energy to create them. And that takes us to the most extreme environments in the universe. If heavier quarks cannot survive in ordinary matter, you might wonder whether they matter at all. Maybe they are just theoretical artifacts, numbers on a chalkboard, predictions that physicists made to complete their equations, but that have no real presence in the physical universe. That would be wrong. The heavier quarks are not theoretical. They are not abstractions. Every single one of them has been produced, detected, measured, and studied in extraordinary detail. They show up in violent collisions, in the debris of cosmic events, and in the extreme conditions of the early universe itself. They are born constantly, in laboratories, in the upper atmosphere, in the hearts of collapsing stars. They are as real as the chair you are sitting in. The difference is that they do not last. They appear, they participate in the drama of particle physics, and then they are gone, transformed, decayed into lighter particles. Their existence is measured not in seconds or even milliseconds, but in trillionths and quadrillionths of a second. Brief beyond comprehension, but absolutely, undeniably real. The story of how physicists discovered these fleeting quarks is one of the greatest detective stories in the history of science. It began not in a laboratory, but in the sky. In the 1930s and 40s, physicists were studying cosmic rays, high-energy particles that rain down on Earth constantly from space. These particles originate from violent astrophysical events, supernova explosions, the jets of material blasting out from regions near black holes. When these particles slam into the upper atmosphere, they collide with nitrogen and oxygen nuclei and produce showers of secondary particles that cascade down toward the ground. By placing detectors on mountaintops or sending them up in balloons, physicists could study what came out of these collisions. And what they found was strange, literally strange. In 1947, physicists George Rochester and Clifford Butler at the University of Manchester were examining cloud chamber photographs of cosmic ray events. Cloud chambers were early particle detectors that made charged particles visible as trails of tiny droplets. Rochester and Butler noticed something unusual. Among the expected tracks of familiar particles, there were V-shaped patterns, 2 tracks diverging from a single point, as if an invisible particle had travelled some distance and then decayed into 2 visible ones. The invisible particle left no track because it was electrically neutral, but its decay products were charged and visible. These were kaons, though that name came later. The strange thing about kaons, the property that gave the strange quark its name, was that they were produced quickly but decayed slowly. In particle physics, if a particle is produced through a particular force, it usually decays through the same force at a comparable rate. Kaons were clearly produced in strong force collisions, which happen on timescales of roughly 10 to the negative 23 seconds. But kaons lived for roughly 10 to the negative 8 seconds before decaying. That is 1,000 trillion times longer than expected. Something was preventing them from decaying through the strong force. They had to decay through a different, much weaker interaction. This puzzling behavior was labeled strangeness, and the internal property that caused it was called the strange quantum number. What physicists eventually understood, once the quark model was developed in the 1960s, was that kaons contained a type of quark that was not present in ordinary protons and neutrons. They contained the strange quark. A kaon is a meson, meaning it consists of one quark and one antiquark. A positive kaon is made of an up quark and an anti-strange quark. A neutral kaon is made of a down quark and an anti-strange quark, or vice versa. The strange quark inside the kaon is what made the particle behave oddly. It gave the kaon a quantum number, strangeness, that the strong force conserves. The strong force can create strange quarks, but only in pairs. A strange quark and an anti-strange quark produced together. This means the strong force cannot destroy a single strange quark on its own, because that would violate strangeness conservation. Only the weak force, which does not conserve strangeness, can change a strange quark into an up or down quark, and the weak force is slow compared to the strong force. So the kaon lives a relatively long time, waiting for the weak force to finally transform its strange quark into something lighter. This was the first glimpse of a heavier quark showing up in the real world, not in a theory, not in an equation, in a cloud chamber on a mountaintop, captured on photographic film. Cosmic ray collisions had enough energy to pull strange quarks out of the vacuum, package them into kaons, and send those kaons streaking through the atmosphere. The kaons existed for roughly a 10 millionth of a second before decaying, but that was long enough to leave a visible track, long enough to be discovered. Strange quarks turned out to be common in high-energy physics. Every particle accelerator that reached sufficient energy produced kaons in abundance. But the story did not stop there. If nature had 3 quarks, up, down, and strange, were there more? Some theoretical arguments suggested there should be a 4th. In 1970, physicists Sheldon Glashow, John Iliopoulos, and Luciano Maiani proposed that a 4th quark must exist, based on mathematical consistency requirements in the theory of weak interactions. Without a 4th quark, certain processes that had never been observed would be predicted to occur at measurable rates. With a 4th quark, these processes would be suppressed, exactly matching what experiments showed. The predicted 4th quark was named the charm quark. But predicting a particle and finding it are two very different things. The discovery came in November of 1974, and it happened in the most dramatic way possible. 2 research groups, working independently at different laboratories using completely different experimental techniques, discovered the same particle at almost exactly the same time. At the Stanford Linear Accelerator Center in California, a team led by Burton Richter was colliding electrons with their antiparticles, positrons, and carefully scanning different collision energies. They were methodically increasing the energy of the collisions, step by step, recording what came out at each energy level. When they reached an energy corresponding to about 3.1 giga-electron volts, something extraordinary happened. The rate of particle production spiked dramatically. The number of particles emerging from collisions increased by a factor of roughly 100 compared to neighboring energies. This was not a gradual increase. It was a sharp, narrow peak, a resonance. It meant that at this specific energy, the electron and positron were creating a new particle that then decayed into the observed products. Richter's team called this particle the psi. At Brookhaven National Laboratory in New York, a team led by Samuel Ting was conducting a very different experiment. They were firing high-energy protons at a beryllium target and looking for pairs of electrons and positrons emerging from the debris. After years of painstaking work, carefully filtering signal from enormous backgrounds of noise, Ting's team found a clear peak at the same mass, about 3.1 giga-electron volts. They called their particle the J. The contrast between the two experiments could hardly have been sharper. Richter's discovery was almost accidental in its timing. His team had been methodically scanning collision energies, stepping through them one by one, looking for anything unusual. On the morning of November 11, 1974, they reached 3.1 giga-electron volts, and the signal was so dramatic that the experimenters initially suspected an equipment malfunction. Detectors do not normally show a 100-fold spike in production rate from one energy step to the next. Something had to be wrong with the apparatus. They checked the equipment, they recalibrated, they repeated the measurement. The spike was still there, sharp, narrow, unmistakable. Within hours, the team knew they had found something extraordinary. The particle was incredibly narrow in its energy width, meaning it lived a surprisingly long time before decaying. Roughly 1,000 times longer than expected for a particle of that mass decaying through the strong force. Whatever this object was, something was preventing it from falling apart quickly. Something new was at work inside it. Ting's path to the same particle had been entirely different. He had conceived his experiment years earlier, convinced that undiscovered heavy particles might be lurking at masses that previous experiments had failed to probe. He designed a specialized detector at Brookhaven capable of picking out rare electron-positron pairs from an overwhelming flood of background particles. For every event his team wanted, millions had to be filtered away. Ting also had a reputation for secrecy. He kept his results closely guarded, sharing them with almost no one outside his immediate team, insisting on checking and rechecking every measurement before making any public announcement. By the autumn of 1974, his group had accumulated enough data to see the peak clearly. A sharp resonance at 3.1 giga-electron volts. The same particle Richter had found on the other side of the continent, using a completely different method. The near-simultaneous announcement sent shockwaves through the physics community. Within days, laboratories around the world scrambled to confirm the result. At the Frascati laboratory in Italy, physicists operating an electron-positron collider reproduced the signal almost immediately. At the German electron synchrotron laboratory in Hamburg, confirmation followed shortly after. The particle was real. It existed at exactly the mass both teams had reported, with exactly the properties both teams had measured. The speed of confirmation was unprecedented. Experimenters who had been working on unrelated projects dropped everything to search for the new particle. It was as if someone had shouted fire in a building full of physicists. Everyone ran toward the flame. And the discoveries did not stop at the J psi itself. Within days of the initial announcement, Richter's team at SLAC found a second, heavier version of the same particle at a mass of about 3.7 giga-electron volts. This was the psi prime, an excited state of the charm-anti-charm system. More related particles followed over the next several months. An entire family of charm-anti-charm bound states emerged, each at a specific predicted mass, each with specific predicted properties. The quark model had not just predicted one particle, it had predicted an entire spectrum, and that spectrum was being confirmed point by point. It was like discovering a new element and then immediately finding an entire row of the periodic table that no one had known existed. The November Revolution earned its name not just because it happened in November, but because it genuinely overturned the established order. Before the J psi, the quark model was a promising hypothesis. After it, the quark model was settled science. When the two teams learned of each other's results, the physics world erupted. The particle was named the J psi, honoring both discoveries. And its identity was quickly established. It was a meson made of a charm quark and an anti-charm quark, bound together by the strong force. The charm quark had been found. The fourth flavor was real. The impact was seismic. Physicists called it the November Revolution because it changed everything almost overnight. Before the J psi, the quark model was still somewhat controversial. Some physicists believed quarks might be purely mathematical tools rather than physical objects. The discovery of charm, the fourth quark, arriving exactly where theory predicted it should be, with precisely the properties theory demanded, convinced nearly everyone. Quarks were real. The quark model was correct, and the standard model, still being assembled at the time, received one of its most powerful confirmations. Richter and Ting shared the Nobel Prize in 1976 for the discovery. The charm quark opened the door. If 4 quarks existed, could there be more? Theoretical work was already suggesting the answer was yes. Kobayashi and Muskawa had shown in 1973 that explaining a subtle asymmetry observed in kaon decays, a phenomenon called CP violation, required at least 3 generations of quarks. Not 2, 3. That meant 6 quarks total. 2 had already been found in ordinary matter. The strange and charm quarks had been discovered in experiments. That left 2 more. A third generation, the bottom and the top. The bottom quark came first. In 1977, a team led by Leon Lederman at Fermilab near Chicago discovered a new particle called the upsilon. They were colliding protons with atomic nuclei at high energies and examining the pairs of muons that emerged. Muons are heavier cousins of electrons, and pairs of them can be produced when certain heavy particles are created and immediately decay. Lederman's team found a clear resonance at a mass of about 9.5 giga-electron volts. The upsilon was a meson made of a bottom quark and an anti-bottom quark, bound together by the strong force. It was the same pattern as the J psi, but heavier. A new quark flavor had revealed itself. The bottom quark, sometimes also called the beauty quark, was the 5th flavor. Its discovery confirmed that a third generation existed, and if the Kobayashi-Muskawa prediction was correct, there had to be a 6th quark to complete the pair. The partner of the bottom quark. The top quark. Finding the top quark turned into one of the longest and most expensive hunts in the history of particle physics. The problem was mass. Each successive quark generation had been dramatically heavier than the one before. The up quark weighs about 2 mega-electron volts. The charm quark weighs about 1,270 mega-electron volts. If the pattern continued, the top quark could be enormously heavy. And it was. Far heavier than anyone initially expected. Throughout the 1980s and into the 1990s, physicists at accelerators around the world searched for the top quark. Each time they increased their collision energy and failed to find it, they knew it had to be heavier than they had reached. The lower bound on the top quark mass kept climbing. 10 giga-electron volts, 20, 50, 80, 100. The top quark was stubbornly refusing to appear because no accelerator on Earth had enough energy to create it. Finally, the Tevatron at Fermilab had the power. The Tevatron was a proton-antiproton collider with a center of mass collision energy of 1.8 tera-electron volts, the most powerful accelerator in the world at the time. 2 massive detector experiments, CDF and D0, sifted through billions of collisions, searching for the telltale signature of top quark production and decay. In March of 1995, both experiments simultaneously announced the discovery of the top quark, with a mass of approximately 173 giga-electron volts. The physics community had been waiting for almost 2 decades. The top quark completed the Standard Model's quark sector. 6 flavors, 3 generations. The pattern was finished. Every quark that the theory required had been found in nature. But what do these heavier quarks actually do once they are created? They form composite particles, just as up and down quarks do. Strange quarks form kaons and other strange hadrons.
Charm quarks form d mesons, particles made of a charm quark paired with a lighter antiquark, or vice versa. Bottom quarks form b mesons, particles made of a bottom quark and a lighter antiquark. These composite particles are real, tangible objects that leave visible tracks in detectors. They have measurable masses, measurable lifetimes, measurable decay patterns. Physicists have studied millions of them, but every single one of these particles is temporary. They live for picoseconds at most, trillionths of a second, timescales we already traced in the decay cascades earlier. What matters here is what that brevity looks like inside a detector. A B meson produced in a collision at the Large Hadron Collider flies a few millimeters from the point where it was created before it decays. A few millimeters. That is all the distance a bottom quark ever gets to travel before the weak force transforms it into something lighter and the composite particle falls apart. Physicists detect these particles not by seeing them directly, but by noticing that their decay products originate from a point slightly displaced from the collision vertex. That tiny displacement, that gap of a few millimeters between where the collision happened and where the decay products appear, is the entire visible signature of a bottom quark's existence. Despite their brief lives, B mesons and D mesons have been extraordinarily useful to physics. Entire facilities have been built specifically to produce and study them. The B factories, electron-positron colliders designed to create B mesons by the billions, operated in Japan and the United States throughout the 2000s. These experiments measured the decays of B mesons with exquisite precision, testing the predictions of the CKM matrix, searching for violations of fundamental symmetries, and probing the structure of the weak force. The study of these short-lived particles has led to Nobel Prizes and deepened our understanding of why the universe contains more matter than antimatter. And then there is the top quark, which, as we discussed, decays so fast that it never forms a composite particle at all. It is produced in high-energy collisions at the Large Hadron Collider at CERN and at the now-retired Tevatron. It exists for less time than the strong force needs to form a single bond, then decays into a bottom quark and a W boson. Physicists study the top quark not by observing it directly, but by analyzing the spray of particles its decay produces. Every top quark ever studied has been a forensic reconstruction, a crime scene assembled from the debris left behind after the quark has already vanished. But particle accelerators are not the only places where heavy quarks appear. They are also created in the upper atmosphere every day. Cosmic rays, those high-energy particles from deep space, slam into atmospheric nuclei at energies that can exceed anything achievable in human-built accelerators. The most energetic cosmic rays carry more energy in a single particle than a professional tennis serve. When these particles collide with nitrogen or oxygen atoms in the atmosphere, they produce cascading showers of secondary particles. Among those secondaries are kaons and other strange hadrons. Some cosmic ray events have enough energy to produce charm quarks as well. These particles rain down through the atmosphere, decaying as they fall, producing muons and neutrinos that reach the ground and even penetrate deep underground. Every minute, roughly 10,000 muons pass through every square meter of the Earth's surface, many of them the distant descendants of strange and charm quarks created in cosmic ray collisions high in the atmosphere. The heavy quarks themselves are long gone, decayed within microseconds of their creation, but their decay products are everywhere. There is one more environment where all 6 quark flavors once existed together, freely, in enormous numbers.
the early universe itself. In the first moments after the Big Bang, the universe was unimaginably hot and dense. Within the first microsecond, the temperature exceeded 2 trillion degrees. At these temperatures, matter existed in a state unlike anything found naturally in the universe today. Protons and neutrons could not form. The energy was too high. The temperature was too intense. Individual quarks and gluons moved freely in a seething plasma, colliding, interacting, creating and annihilating in an endless frenzy of activity. This state of matter is called a quark-gluon plasma. In a quark-gluon plasma, confinement does not apply. The quarks are not locked inside hadrons. They roam freely through the plasma, interacting with gluons and with each other. And at the temperatures present in the first microsecond of the universe, there was more than enough energy to create quarks of every flavor. Up and down quarks were the most abundant because they are the lightest and therefore the easiest to create. But strange quarks were also plentiful. Charm quarks appeared in significant numbers. Bottom quarks popped in and out of existence. Even top quarks, the heaviest of all, were present in the earliest instance when temperatures were at their most extreme. Try to picture what this environment was actually like. The entire observable universe, everything that would eventually become hundreds of billions of galaxies, trillions of stars, and countless planets, was compressed into a region smaller than our present-day solar system. And it was hot beyond anything that exists in the universe today. 2 trillion degrees is not a temperature you can compare to anything familiar. The surface of the Sun is about 5,500 degrees. The core of the Sun, where nuclear fusion occurs, reaches about 15 million degrees. The center of the most massive stars, just before they explode as supernovae, reaches a few billion degrees. 2 trillion degrees is hundreds of times hotter than the core of an exploding star. At this temperature, matter cannot hold itself together in any recognizable form. Atoms are impossible. Nuclei are impossible. Even individual protons and neutrons cannot maintain their structure. The thermal energy surrounding every particle is so enormous that the bonds holding quarks inside hadrons are overwhelmed. The strong force, the most powerful force in nature at short distances, cannot confine quarks at these temperatures. The quarks break free. The density was equally extreme. At temperatures around 2 trillion degrees, the energy density of the plasma was roughly 10 to the 35 joules per cubic meter. Every cubic centimeter of space contained trillions of times more energy than a modern nuclear weapon yields in its entirety. Quarks and gluons were packed so tightly that the average distance between them was smaller than the diameter of a proton. They were overlapping, colliding, interacting thousands of times in the span of a single proton crossing time. The plasma was not a calm sea of particles drifting past each other. It was a violent, seething maelstrom, a storm of creation and annihilation happening at nearly the speed of light. In this environment, the concept of an individual particle starts to lose its meaning. A quark would form, interact with gluons, collide with another quark, produce a burst of energy that spawned new quark-antiquark pairs, and those pairs would immediately interact and transform in turn. The identities of particles flickered constantly. An up quark might absorb a gluon and radiate another. A high-energy gluon might spontaneously split into a bottom quark and an anti-bottom quark, which would exist for a fleeting instant before annihilating back into gluons. The plasma was a democracy of violence. Every particle type that the available energy could produce was being produced, destroyed, and produced again in an endless, frenetic cycle. No particle lasted long. No configuration was permanent. Everything was in flux. This was the only moment in the history of the universe when all 6 quark flavors existed in thermal equilibrium. Not confined to a detector for a trillionth of a second, not appearing in a single isolated collision event. Everywhere, filling all of space. The heavier the quark, the rarer it was at any given instant,
because producing a top quark at 173 giga-electron-volts required borrowing more from the thermal budget than producing an up quark at 2 mega-electron-volts. But even the top quark was present in meaningful numbers during the very hottest instants, when the temperature was high enough to make its production routine rather than exceptional. For a window of time measured in fractions of a microsecond, the universe was a place where every quark flavor mattered. For a brief, blazing moment, all 6 flavors coexisted. The universe was a democratic place, where no quark was favored over another. Every flavor was being constantly created from the enormous thermal energy of the plasma and constantly annihilating back into energy. The heavier the quark, the rarer it was at any given moment, because more energy was needed to produce it. But all 6 were present. All 6 were participating. Then the universe cooled. As space expanded, the temperature dropped. When it fell below roughly 2 trillion degrees, the quark-gluon plasma underwent a phase transition. Quarks could no longer roam freely. The strong force asserted itself. Quarks were confined into hadrons. Protons and neutrons formed for the first time. And as the temperature continued to drop, the heavy quarks that had been sustained by the intense thermal energy could no longer be produced. Their creation rate plummeted, but their decay rate did not. The strange, charm, bottom and top quarks, still present in the plasma, decayed rapidly through the weak force, cascading down the mass hierarchy exactly as they do in particle accelerators today. Within a few microseconds, the heavy quarks were gone, decayed, transformed into up and down quarks that were promptly confined into protons and neutrons. This phase transition, from quark-gluon plasma to hadronic matter, was one of the most important events in cosmic history. It determined the composition of the universe. Before it, all 6 flavors existed. After it, only 2 remained. The universe went from a hot, symmetric state where every quark type was present to a cold, asymmetric state where ordinary matter is built exclusively from the lightest pair. The 4 heavier quarks were not destroyed. They were not removed from the laws of physics. They simply decayed. The universe cooled past the point where they could be sustained, and the weak force did the rest. Remarkably, physicists have managed to recreate quark-gluon plasma in the laboratory. At the relativistic heavy ion collider, known as RHIC, at Brookhaven National Laboratory, and at the Large Hadron Collider at CERN, physicists collide heavy nuclei, typically gold or lead atoms, at nearly the speed of light. When these nuclei slam together, the collision zone reaches temperatures exceeding 4 trillion degrees for a fleeting instant. For a brief moment, on a tiny scale, the conditions of the early universe are reproduced. Quarks and gluons are deconfined. A droplet of quark-gluon plasma forms. Experiments like ALICE at the Large Hadron Collider study the properties of this plasma, measuring how it flows, how particles are produced within it, and how it cools and transitions back into ordinary hadrons. These experiments have confirmed that quark-gluon plasma behaves as an almost perfect liquid, flowing with remarkably little internal friction. The plasma expands, cools, and hadronizes within roughly 10 to the negative 23 seconds. Then the hadrons fly outward and are captured by detectors.
By analysing these hadrons, physicists reconstruct what happened inside the tiny fireball and learn about the state of matter that filled the entire universe in its first moments. So, the 4 heavier quarks are not absent from the universe. They are absent from stable matter, which is a very different statement. They appear in cosmic ray showers in the atmosphere. They are produced by the trillions in particle accelerators around the world. They existed in enormous numbers in the first microsecond of the universe. They are created in the extreme environments around neutron stars and black holes, wherever nature concentrates enough energy to pull heavy quarks from the vacuum. They show up in the showers of particles produced when ultra-high energy neutrinos from distant astrophysical sources interact with matter deep inside the Earth. They are everywhere that extreme energy is present, but they never stay. That is the defining characteristic of the heavier quarks. They are produced easily enough. Nature has no prohibition against creating them. Any collision with sufficient energy can bring a heavy quark into existence. The strong force, electromagnetism, and the weak force all participate in processes that produce them. But once produced, their enormous mass compared to the up and down quarks makes their decay through the weak force inevitable and rapid. They appear for their allotted fraction of a second, and then they are gone, their mass converted back into kinetic energy and lighter particles. This is not a flaw. It is not a waste. The heavier quarks play essential roles in the physics of the universe. Their existence and their properties shape the structure of the Standard Model. Their decays reveal deep truths about the symmetries and asymmetries of nature. The study of kaons led to the discovery of CP violation, the subtle difference between the behavior of matter and antimatter that may explain why the universe contains matter at all, rather than being an empty void of pure radiation. The study of B mesons refined our understanding of CP violation and confirmed predictions of the CKM matrix with extraordinary precision. The top quark's enormous mass makes it a unique laboratory for studying the Higgs field, the mechanism that gives all fundamental particles their mass. Because the top quark couples to the Higgs field more strongly than any other known particle, studying its properties teaches us about the Higgs mechanism itself. Every one of the four heavier quarks has contributed something irreplaceable to our understanding of nature. Strange quarks taught us about symmetry and its breaking. Charm quarks confirmed the quark model and the reality of quarks as physical objects. Bottom quarks revealed the third generation and the full scope of the CKM matrix. The top quark, the last piece of the puzzle, completed the picture and provided a unique window into the origin of mass. They are not unnecessary. They are not decorative. They are not mistakes. They are fundamental pieces of the architecture of reality. But they are transient pieces. They flash into existence when energy permits. They participate briefly in the processes that govern the subatomic world, and then they decay, leaving behind the only quarks light enough to endure. Up and down, always up and down. The survivors, the builders. But knowing that up and down quarks are the last quarks standing raises a deeper question. Why are protons and neutrons specifically the structures that survive? 6 quarks decay to 2, but those 2 quarks could in principle form many different kinds of composite particles. What makes the proton and the neutron so special? What makes them the particular combinations that build every atom in the observable universe and persist for billions upon billions of years? That is the question of stability itself, and it takes us to the deepest layer of the answer.
We have established that 6 quark flavors exist, and that the 4 heaviest decay rapidly through the weak force, cascading down the mass ladder until only up and down quarks remain. But this alone does not fully answer our question. Having only up and down quarks available does not automatically guarantee that protons and neutrons are the things that get built. Up and down quarks could, in principle, combine in many different ways. They could form countless varieties of composite particles. So why do we end up with specifically protons and neutrons? Why are these 2 particular arrangements of quarks the ones that persist for billions of years, forming every atomic nucleus in every star and planet across the observable universe? The answer lies in a principle so fundamental that it governs nearly everything in physics. Nature seeks the lowest available energy state, and among all the particles that up and down quarks can form, the proton and the neutron sit at the bottom. To understand this,
we need to think carefully about what determines which composite particles can exist and which ones survive. First, there is a rule about color. We discussed earlier that quarks carry color charge and that only color-neutral combinations are permitted to exist as free particles. This constrains what quarks can do. You cannot have a particle made of two quarks because two color charges cannot combine to make a neutral state. You need either three quarks, one red, one green, one blue, which produces a baryon, or one quark and one antiquark with matching color and anticolor, which produces a meson. There are also more exotic possibilities that physicists have explored. Tetraquarks made of two quarks and two antiquarks, pentaquarks made of four quarks and one antiquark. Some of these have been observed in recent years at the Large Hadron Collider, but they are all extremely unstable. They decay almost immediately into more conventional hadrons. The workhorses of the universe, the particles that actually persist long enough to matter, are the simplest color-neutral combinations: baryons and mesons. Now consider mesons. A meson is made of one quark and one antiquark. Using only up and down quarks and their antiparticles, you can build several types of mesons. The most common are pions. A positive pion is made of an up quark and an anti-down quark. A negative pion is the reverse. A neutral pion is a quantum mixture of up anti-up and down anti-down pairs. Pions are the lightest mesons. They have masses of about 135 to 140 mega-electron volts. But pions are unstable. A charged pion lives for roughly 26 nanoseconds. A neutral pion lives for only about 84 attoseconds, an almost incomprehensibly short time. Pions decay into muons, neutrinos, and photons. They do not persist. They cannot form the building blocks of stable matter. No meson can. Every meson is unstable because a quark and an antiquark sitting together will eventually annihilate each other or rearrange themselves through the forces available to them. Mesons are inherently temporary. So stable matter must be made of baryons. Three quarks bound by the strong force into a color-neutral state. Using only up and down quarks, how many different baryons can you build? The answer depends on how many ways you can combine three quarks chosen from two flavors. The simplest combinations are the proton, two up quarks and one down quark, and the neutron, one up quark and two down quarks. But there are others. You could put three up quarks together or three down quarks together. These particles exist. Three up quarks form a particle called the delta plus plus. Three down quarks form the delta minus. These are real particles that have been produced and studied in accelerators. But they are extremely unstable. The delta plus plus has a lifetime of roughly 5 × 10 to the negative 24 seconds. It decays almost instantly into a proton and a pion. The delta minus decays into a neutron and a pion on the same timescale. These particles are not even close to stable. They exist for barely longer than the time it takes light to cross a single proton. Why are the delta particles so unstable while the proton and neutron are not? The answer is mass and spin configuration. The delta particles have higher mass than the proton and neutron, despite being made of the same quarks. This is because the quarks inside a delta are arranged with their spins aligned in the same direction, which puts them in a higher energy state. In a proton or neutron, the quark spins are arranged differently, partially cancelling, which lowers the total energy. The delta particles sit at a higher rung on the energy ladder. They can decay to the lower rung, the proton or neutron, by emitting a pion. And they do, almost instantly. There is nothing stopping them. The energy is available. The decay is allowed by all conservation laws, so it happens at the speed the strong force can manage.
which is extraordinarily fast. The proton and the neutron, by contrast, sit at the bottom of the baryon mass hierarchy. The proton has a mass of about 938.3 megaelectronvolts. The neutron is slightly heavier at about 939.6 megaelectronvolts. No baryon made of up and down quarks is lighter than these two. There is nowhere for them to fall. The proton cannot decay into a lighter baryon by emitting a pion, because no lighter baryon exists. The neutron can decay into a proton, because the proton is slightly lighter. But this is a weak force process, not a strong force process, and it is very slow compared to the delta's decay. The proton is the lightest baryon, period. It has the lowest mass of any three-quark combination allowed by the laws of physics. It sits at the absolute bottom of the energy ladder for baryonic matter. And that is why it survives. But there is another critical ingredient in the proton's extraordinary stability. It is called baryon number conservation. Every quark carries a baryon number of plus 1/3. Every antiquark carries minus 1/3. A baryon has a total baryon number of plus 1. A meson has a baryon number of 0. In all observed interactions, across every experiment ever conducted, baryon number is conserved. It never changes. You can create quark-antiquark pairs or transform one baryon into another, but the total baryon number always stays the same. You cannot destroy a baryon entirely. You cannot turn a proton into pure radiation. That would change the baryon number from 1 to 0, violating conservation. This is why the proton appears to be absolutely stable. It is the lightest baryon. It cannot decay into a lighter baryon because none exists. And it cannot simply disappear because baryon number conservation forbids it. The proton is trapped by these two constraints simultaneously. It has nowhere to go. It has no allowed decay channel. It is locked in place at the bottom of the hierarchy, permanently. How stable is the proton? Extraordinarily. Experimentally, physicists have searched for proton decay for decades using massive underground detectors. The most famous is Super Kamiokande, a detector located deep beneath the mountains of Kamioka, Japan. Super Kamiokande contains 50,000 tons of ultra-pure water, surrounded by roughly 11,200 photomultiplier tubes, sensitive enough to detect a single photon. If a proton decays, the resulting particles will move through the water faster than light travels through water, producing a faint cone of light called Cherenkov radiation. The tubes would catch it, and physicists would have caught a proton in the act of dying. Super Kamiokande has been watching protons since 1996. 50,000 tons of water contains on the order of 10 to the 34 protons. That is an enormous number of protons, each one being monitored for any sign of decay. Despite watching this many protons for decades, not a single proton decay has ever been observed. This allows physicists to set a lower bound on the proton's lifetime. Current limits exceed 10 to the 34 years for the most commonly predicted decay channels. To put that number in perspective, the universe is approximately 13.8 billion years old, which is about 1.4 times 10 to the 10 years. The proton's lifetime is at least 10 to the 24 times longer than the current age of the universe. If you wrote down the age of the universe and then multiplied it by 1 trillion, and then multiplied that by another trillion, you would still not reach the lower bound on the proton's lifetime. The proton is, for all practical purposes, eternal. Some theoretical frameworks called grand unified theories predict that the proton should eventually decay at some extraordinarily slow rate. These theories attempt to unify the strong, weak, and electromagnetic forces into a single unified interaction at extremely high energies. In some versions, baryon number is not perfectly conserved, but is very slightly violated,
allowing protons to decay into lighter particles like positrons and neutral pions over immense timescales. The earliest and simplest grand unified theory, based on a mathematical structure called SU5, predicted a proton lifetime of roughly 10 to the 31 years. Super Kamiokande ruled this out by the late 1990s. More sophisticated theories predict longer lifetimes, some as long as 10 to the 36 years or beyond. Hyper Kamiokande, a next-generation detector currently under construction in Japan, will contain roughly 260,000 tons of water and will push the experimental limits even further. If proton decay exists at rates predicted by these theories, Hyper Kamiokande may find it. If it does not, the proton might be truly immortal. Either outcome would reshape our understanding of particle physics. But even if the proton eventually decays at some unimaginably slow rate, for all practical purposes, it is stable. On timescales relevant to atoms, to molecules, to stars, to planets, to life, the proton does not decay. It persists. And because it persists, it can serve as the foundation of matter. Every hydrogen atom in the universe contains one proton that has existed since roughly 1 microsecond after the Big Bang, when protons first formed from the cooling quark-gluon plasma. Those protons are still here, nearly 14 billion years later, unchanged. That is stability of a kind that no other baryon can match. Now let us consider the neutron again. The neutron is the other building block of nuclei, but its story is more complicated. We already know what happens to a free neutron. Left alone in empty space, it decays. One of its down quarks transforms into an up quark through the weak force, and the neutron becomes a proton. The process takes an average of about 14 minutes and 40 seconds, slow by particle physics standards, because the mass difference between neutron and proton is so tiny. And we already know what saves the neutron inside a nucleus. The binding energy of the strong force changes the energy landscape so that the decay is no longer favorable. The neutron is locked in place, not by anything intrinsic to the neutron itself, but by the nuclear environment surrounding it. What we have not yet explored is what this tells us about the architecture of matter at a deeper level. The neutron's conditional stability reveals something remarkable about how finely balanced the universe is. The mass difference between the neutron and the proton is about 1.3 mega-electron volts. That is tiny. It is less than 1/7 of 1% of the neutron's total mass. If this difference were significantly larger, say 10 or 20 mega-electron volts, instead of 1.3, neutrons would decay so rapidly and so energetically that nuclear binding could not compensate. No nucleus could stabilize a neutron. The universe would contain only protons. No neutrons means no deuterium. No deuterium means the nuclear reactions that build helium in the first minutes after the Big Bang could not proceed. Without helium, the chain of nucleosynthesis that eventually produces carbon, oxygen, and iron inside stars would be fundamentally altered. The periodic table, as we know it, would not exist. If the difference ran the other way, if the proton were heavier than the neutron by a comparable margin, the consequences would be even more catastrophic. Protons would decay into neutrons. Hydrogen, the most abundant element, the fuel of stars, the essential ingredient of water, would be unstable. The universe would be a dark, cold place, filled with neutrons and neutrinos and very little else. No atoms, no chemistry, no stars, no light. The fact that the neutron is only slightly heavier than the proton, by just enough to make free neutrons unstable, but not so much that nuclear binding cannot compensate, is one of the most striking balances in all of physics. It is not explained by the Standard Model. The Standard Model can accommodate the quark masses that produce this difference, but it does not predict them. They are inputs measured by experiment. Why the down quark is roughly 2.5 mega-electron-volts heavier than the up quark, just enough to make the neutron marginally heavier than the proton, is an open question. Some physicists regard it as evidence of fine-tuning. Others regard it as something a deeper theory will eventually explain. Either way, it is the reason neutrons can serve as building blocks of nuclei rather than being permanently unstable or permanently dominant. This is a profound example of how context determines stability. The same particle, the neutron, is unstable in one environment and stable in another. Free neutrons decay in minutes. Bound neutrons inside iron or carbon or oxygen nuclei persist for billions of years. The particle has not changed. Its internal structure is identical. What changed is the energy landscape around it. And that landscape is shaped by the strong force, by the number and arrangement of neighboring nucleons, and by the specific balance of forces within each nucleus. The interplay between these forces determines which nuclei are stable and which are radioactive. In nuclei with too many neutrons relative to protons, some neutrons find themselves in energy states where decay is favorable, even accounting for binding energy. These neutrons decay, converting into protons and shifting the nucleus toward a more balanced ratio. This is beta-minus decay, and it is one of the most common forms of radioactivity. In nuclei with too many protons, the reverse can happen. A proton converts into a neutron through beta-plus decay, emitting a positron and a neutrino. Nature constantly adjusts the ratio of protons to neutrons inside nuclei, nudging them toward the configuration with the lowest total energy. The valley of stability, as physicists call it, is a narrow band on the chart of nuclides where the proton-to-neutron ratio produces the most tightly bound, lowest energy configurations. Nuclei in this valley are stable. Nuclei outside it are radioactive, decaying until they reach the valley. All of this, the stability of protons, the conditional stability of neutrons, the existence of the valley of stability, the binding energy that holds nuclei together, rests on up and down quarks. These two flavors, and only these two flavors, produce the particles that can form stable nuclei. If you tried to build a nucleus using strange quarks, you would need strange baryons. A lambda particle, for instance, contains an up quark, a down quark, and a strange quark. Lambda particles have been produced in abundance, but they decay in roughly 2.6 times 10 to the negative 10 seconds. You cannot build a nucleus from particles that vanish in less than a nanosecond. The strange quark inside the lambda decays through the weak force into an up quark, and the lambda becomes a proton or a neutron plus a pion. Once again, the heavy quark is filtered out. Only up and down quarks remain. Physicists have searched for something called strange matter, hypothetical nuclear material containing roughly equal numbers of up, down, and strange quarks. Some theoretical calculations have suggested that, under extreme conditions, particularly at the enormous densities found inside neutron stars, strange matter might actually be more stable than ordinary nuclear matter. If true, this would be extraordinary. It would mean that ordinary matter is not the true ground state, but merely a metastable state, stable enough to last for billions of years, but not the absolute lowest energy configuration. Neutron stars might contain cores of strange matter, or even be entirely composed of it. Some theorists have speculated that strange matter could be absolutely stable, meaning that a lump of it would not decay, and could theoretically convert ordinary matter it touched into more strange matter. This remains highly speculative. No evidence for stable strange matter has ever been found. Experiments at heavy ion colliders have searched for strangelets, tiny droplets of strange matter that might be produced in collisions. None have been detected. The hypothesis is fascinating but unconfirmed. For all we know, ordinary nuclear matter made of protons and neutrons, composed exclusively of up and down quarks, is indeed the true ground state of baryonic matter. And that brings us back to our central answer. Let us now state that answer clearly and completely. The universe contains 6 quark flavors. All 6 are real. All 6 have been experimentally confirmed. All 6 are required by the Standard Model. Not optional, not decorative. Mathematically necessary. The 6 flavors are arranged in 3 generations of increasing mass. Up and down in the first generation, charm and strange in the second, top and bottom in the third. Each generation mirrors the charge structure of the ones before it, but each successive generation is dramatically heavier. Ordinary stable matter, the matter that makes up atoms, molecules, planets, stars, and living beings, is built exclusively from up and down quarks. Protons contain 2 up quarks and 1 down quark. Neutrons contain 1 up quark and 2 down quarks. Every atomic nucleus in the observable universe is made of protons and neutrons. No stable atom contains charm, strange, bottom, or top quarks. The reason is not that the heavier quarks are unreal or unimportant. The reason is that they are unstable. The weak nuclear force, the only force capable of changing one quark flavor into another, transforms heavy quarks into lighter ones whenever the laws of physics permit it. The heavier the quark, the faster it decays. The top quark, the heaviest, decays so rapidly that it cannot even form a composite particle. The bottom, charm and strange quarks form composite particles that exist for tiny fractions of a second before the weak force transforms their heavy quarks into lighter ones. Every decay cascade terminates at up and down quarks. These are the lightest flavors. They have no lighter quarks to decay into. They are the end of every chain, the survivors. Among the composite particles built from up and down quarks, the proton and neutron have the lowest mass. They sit at the bottom of the baryon energy hierarchy. No lighter baryon exists. The proton is additionally protected by baryon number conservation, which forbids its total destruction. The neutron, slightly heavier than the proton, is unstable when free, but is stabilized inside atomic nuclei by the binding energy of the strong force. Together, protons and neutrons form nuclei that persist for billions of years, providing the scaffolding on which all of chemistry, all of geology, all of biology, and all of life is constructed. This is not a story about 4 quarks being unnecessary. It is a story about a filter. The universe creates all 6 quarks freely. It does so in particle accelerators, in cosmic ray collisions, in the quark-gluon plasma of the early universe, in the extreme environments around compact astrophysical objects. All 6 flavors participate in the physics that governs the subatomic world. Strange quarks taught us about symmetry breaking. Charm quarks confirmed the quark model. Bottom quarks revealed CP violation and the full structure of the CKM matrix. The top quark provides a unique window into the Higgs mechanism and the origin of mass. Without the heavier quarks, the Standard Model would be mathematically inconsistent. Certain symmetries would be violated, certain anomalies would go uncancelled. The theory requires 6 flavors. Nature provides 6 flavors. But stability is a filter. It is a sieve through which the entire diversity of the particle zoo is poured, and what comes out the other side is simple. 2 quarks, 2 composite particles, 1 force holding them together. That is enough to build everything. Every element on the periodic table, every mineral, every molecule, every cell, every organism, every star, every planet, every grain of dust drifting between galaxies. All of it traces back to up and down quarks, confined inside protons and neutrons by the strong force, arranged into nuclei by the residual strong interaction, surrounded by electrons held in place by electromagnetism.
The simplicity of this outcome is stunning when you consider the complexity of the underlying rules. The Standard Model contains 17 named fundamental particles, 6 quarks, 6 leptons, 4 force-carrying bosons, and the Higgs boson. It involves 3 fundamental forces with different strengths and ranges, and dozens of measured parameters. The mathematics is among the most sophisticated ever developed by human beings. And yet, after all that complexity plays out, after all the interactions and decays and transformations have finished, what remains is almost absurdly simple. 2 quarks, bound in threes, stacked into nuclei, dressed with electrons. That is an atom. That is matter. That is you. There is something deeply beautiful about this. The universe wrote an elaborate rulebook with 6 flavors of quarks, 3 generations of matter, 4 fundamental forces, and a Higgs field that gives everything mass. Then it ran the rules forward from the Big Bang. Temperatures dropped, heavy quarks decayed, light quarks survived, protons and neutrons formed, nuclei assembled, atoms condensed, stars ignited, planets coalesced, chemistry emerged, biology followed, and eventually, on at least one small rocky planet orbiting an ordinary star in an unremarkable spiral arm of a typical galaxy, matter organized itself into structures complex enough to look back at the rulebook and begin to read it. 6 quarks exist. The universe uses 2, not because the others failed, not because they are flaws in the design, but because mass, decay, and the weak force filter everything down to the lightest, most stable configurations. The 4 heavier quarks play their roles in the instant they exist. They shape the symmetries. They reveal the structure. They participate in the processes that built the universe in its earliest moments. And then they step aside, decaying into the 2 flavors that can endure, up and down. The quiet survivors at the bottom of the hierarchy, the 2 quarks that build the world.